The ultimate problem with the broken ties is probably twofold. Number one, bale loses its original configuration, which makes it more difficult to stack, store, handle, and can affect the bloom height. More importantly than that, when you have broken ties and they're not removed from the bale, you have the risk of damage to the machinery and even more seriously, fire.
If I have a bale that has failed wire or torn packaging, before I can ship it, I have to spend money on it. If I don't do that, then I risk huge expenses of rejections that incorporate all the expenses that are involved in fixing a bale on outbound the way it should have been fixed to start with, plus transportation costs, and potential risk of having to buy a bale because the mill just says, I'm not taking it back.
Now that rejection can come back against the gin. The gin can be held liable for that cost.
Broken ties on cotton bales are a major problem for all segments of the cotton industry. What can ginners do to prevent tie breakage? How can warehousemen reduce broken ties and save on the costs associated with having to repair them? How does the industry deal with growing bale sizes and decreasing densities? First, we need to closely examine the proper way to form and press cotton bales and what measures we can take to prevent excessive tie breakage and the associated costs incurred by ginners, warehousers, shippers, and manufacturers. Dinky presses are used to repair bales at less cost than hand repair. However, if warehouses do not have a dinky press, other methods are employed. For example, workers hand repair the bales by squeezing the bale with forklift clamps and using a ratchet wrench to cinch up a flat band. Regardless of the method used for repairing bales, the size and shape of the repaired bale is never as uniform as a bale with its original ties intact. This non-uniform sized bale will cause handling, storage, and shipping problems. Forklift operation efficiency will decrease, shipping space will be used poorly, and stack stability will decrease. So what are the causes of broken ties? Many different events occur alone or in combination to cause broken ties. The most common of these are excessive platen separation, uneven lint distribution, excessive tie length, incorrect tie placement, and low moisture content. Wire chemistry, while important to tie strength, is not a primary concern with tie breakage. Plastic strapping is prone to damage when it's handled multiple times and may be subject to repairs to restore bales to merchantable conditions. The annual publication Specifications for Cotton Bale Packaging Materials is developed by the Joint Cotton Industry Bale Packaging Committee and adopted by USDA for CCC loan eligibility. The specifications require bale tie manufacturers to test and inspect their wire and certify that each bundle of ties has been formed according to the cotton industry standards. Testing must be performed on wire ties at least once for every 2,000-pound coil of wire. A universal testing machine is used to pull a straight section of wire and a formed knot. If any wire tested does not meet the requirements set forth in the specifications, then the whole coil is rejected. Plastic strapping must be manufactured in accordance with ASTM D3950 standards. Each coil of strapping bears a certification that it has been manufactured according to the specifications. Joints for plastic strapping are fabricated at the gin. These quality control tests are stringent and ensure that poor quality steel or plastic do not enter the bale packaging domain. Compression density and restraint density are the two factors that affect bale tie forces the most. Compression density is the density to which a bale is pressed before it is tied out and released. The restraint density is the density to which the bale settles over time, with ties restraining the bale. The distance of minimum platen separation is the defining factor in compression density. If the minimum practical platen separation is not achieved, the compression density would be too low and the restraining force would be too high. The extra load on each bale could result in tie breakage. Uneven lint distribution can be a big culprit of tie breakage. For example, big-ended bales and big-sided bales can be attributed to incorrect airflow through the battery condenser, improperly designed lint ducts, obstructions, the lint slide angle being too great or too small, improper speed of the lint feeder, or a combination of all these sectors. Tie length is a controlling factor of tie restraint density and therefore possible tie breakage. The maximum tie and strap lengths for GIN universal density bales are 8-wire patterns 89 inches, 6-wire patterns 88 inches, and plastic straps 86 inches. The original strap length and elongation control plastic straps' ending size. Therefore, the size of plastic strap bales is more highly correlated with tie length than wire.
It's important to the industry that we use standard tie lengths on GIN universal density bales for many reasons. Both studies and the practical experience of our manufacturer customers show that by using those standard tie lengths, the bloom height is uniform, which helps them in their automated opening rooms. In addition to that, it helps both warehouses and also the spinner because it allows for more uniform stacking and safer stacking of the cotton in the warehouse, and also loading trucks becomes a much simpler and standard procedure.
Lint that has low moisture content is very springy and much more resilient than lint with a high moisture content. The higher the lint moisture content, the easier the lint will compress and less restraint will be needed to stabilize the bale. Overdrying the lint causes fiber damage and increases press energy consumption. Dry lint increases bale tie forces due to the cotton lint's higher resiliency. Extremely dry lint results in a higher occurrence of wire and strap breakage. Today, GINs with modern moisture monitoring equipment do a better job of adding or removing just the right amount of moisture before raw cotton is processed and the cotton is baled. Using these optimum conditions for a GIN UD bale, we can see the normal forces that 8 ties encounter in restraining a 500-pound bale. The first and 8th ties experience approximately equal forces, which are considerably less than the forces on the middle, 4th, and 5th ties. This indicates that the middle of the normally formed bales exerts more pressure on the ties than the outer or end bale sections. Generally, the average load that a tie on a properly formed bale will undergo is less than 1,500 pounds. Take a look at what happens to GIN UD bale tie loads in worst-case conditions. We need to know how to diagnose problems and what adjustments to make in order to correct the problems. Let's take a look at 3 bales, all 500 pounds with GIN UD dimensions and 89-inch tie lengths. The bales were all pressed with moisture contents of 6% and an even lint distribution. The first bale was pressed to a platen separation of 19 inches, the second to 21 inches, the third to 23 inches. You can see the benefits of bale tie force relief when the bale is pressed to 19 inches, which creates a high compression density and decreases lint fiber resilient forces. Again, we have 3 bales, each weighing 500 pounds with GIN UD dimensions. The bales are all pressed to a platen separation of 19 inches with moisture contents of 6%. 2 bales are pressed with a uniform lint distribution and tied with different lengths of ties, 89 inches and 87 inches. A third bale tied with 87-inch ties happens to be non-uniform in lint distribution. In this case, the tie load on the shorter 87-inch ties is higher than the tie load on the longer 89-inch ties. GIN UD bales dimensions are defined as being bound with ties 87 inches to 89 inches in length. 89 inches is the longest tie available for use. The highest load on bale ties occurs on the non-uniform lint distributed bale. Here, the load will vary at each of the 8 tie positions depending on the amount of lint under each tie. A big-ended bale can cause excessive tie breakage, possibly 4 to 5 ties per bale. Here we have 3 bales side by side, all weighing 500 pounds with Gen UD dimensions, 89-inch tie lengths, normal lint distribution, and pressed to a platen separation of 19 inches. The first bale is pressed at 3% lint moisture content, the second at 6% moisture content, and the third at 8% moisture content. Notice that the tie load decreases with increasing moisture content. Good ginning practices recommend that seed cotton be dried to a moisture content that allows for satisfactory gin processing. Normally, this would mean seed cotton lint moisture in the range of 5.5 to 6% measured at the gin stand. Current moisture restoration technology can be expected only to add 2 to 3% moisture to bales at the press. Therefore, proper moisture content control during the ginning process helps to preserve fiber qualities for the producer and allows the ginner to bale lint with moisture contents in the 7 and 8% range. Lint baled in this moisture range will help avoid the broken ties that can occur with less moisture.
The optimum moisture content at the bale press is 7 to 8%. This moisture level will minimize compression forces and minimize bale tie failure later.
When using wire manually applied to gin standard density and gin universal density bales, it's important for a couple of reasons to rotate the knot from the flat of the bale to the ball or the crown of the bale.
By rotating wire knots to the crown or sample side of the bale from the flat side, we see that the forces of the knots decrease significantly. This relief creates more working knot strength.
In addition to that, getting the knot off the flat of the bale tends to reduce the chance for baggage damage. The bagging tends to hang the knot when it's on the flat, whereas that won't happen as often when it's on the ball. A technique used by many gins to reduce tie breakage in handling is to retrofit the press box and or press doors with strips of metal. This allows the tie to be recessed or indented in the flat part of the bale. As you can see, by doing this, when the forklift comes in and clamps that bale, there is less contact. This greatly reduces tie breakage. It's highly recommended, however, that the manufacturer of the press be consulted before this modification is made.
Remember the main ginning techniques for reducing high stresses on bale ties. Platen separation no greater than 19 to 20 inches. Maintain uniform lint distribution. Tie lengths no greater than 89 inches for 8-wire. Tie lengths no greater than 88 inches for 6-wire. Strap lengths of no greater than 86 inches for plastic strapping. Lint moisture content of 5% to 8% at the press, and rotating the knot to the crown of the bale. Our business requires hard work, but to remain the world's best at packaging cotton, we must always give 110%.